right, so for our last talk of this session, Haowei is going to tell us about synthesis of recursive quantum unitary programs.
Okay. Hi, everybody. I'm Haowei, and now I'm here to present my work. It's about a case for synthesis of recursive quantum unitary programs. And this work, I work with Runzhou, Yuxiang, and Xiaodi. We know that the near-term quantum computers are theoretically very powerful, and we usually hear many theoretics from the news say that the quantum computers can solve some problems that classical computers cannot solve. For example, such as the quantum simulation problems or the integer factorization problems. It has been proved that it is very powerful in theoretically. However, there is still a huge gap between these theoretically powerful quantum computers with the real quantum devices. Because the current quantum devices are very noisy and usually have a very short durations, which makes that the quantum programs, which are usually used by the programmers to utilize these quantum devices, are notoriously very difficult to program. There are two reasons. The first one is that to give a good quantum programs, the programmers usually need to know many unintuitive quantum knowledge. And the second reason is that since the quantum devices are usually very noisy, the quantum programmers usually need to deal with tedium low-level details to maximize their utilized for these quantum devices. So based on this fact, the motivation of our project is that we want to help people to more easily write efficient quantum programs. There are many existing works on this area, and there are many existing circuit synthesize techniques to help people write down some quantum programs. However, all of these prior works are only circuit synthesis, which means that they can only generate a sequence of quantum operations. There is no loop or recursive structure in their programs. They are just a sequence of many quantum operations. And another problem is that there are only some fixed size circuit synthesizers. They usually require the programmers to give the specification as a fixed size matrix or exponential size of input-output vector pair. And then they can only generate some fixed size quantum circuits. So because there is no loop or recursive structure in their synthesized work, this means that their program's lengths will grow with the application size. And another quantum unique problem is that the semantics of quantum operations is usually a matrix related to the application size. So these 2 points make that the synthesized techniques will have an exponential search space and a verification complexity. So these 2 points leads to the result that their synthesized techniques are not very scalable. We have run tests on 2 existing quantum circuit synthesis techniques, and the result shows that they cannot synthesize any results when the application size grows to 6. And the experiment, we time out the experiment in 1 hour, so they fail to synthesize the result in 1 hour when the application size increased to 6. So based on these drawbacks, we want to find a program synthesis framework that can support a loop or recursive structure to enable more large-scale quantum program synthesis. To get such a framework that supports the quantum program synthesis with loop or recursive structure, there are 3 main challenges. The first challenge is that we need a new representation for the specification of quantum programs. All of the existing methods for quantum program synthesis require the user to give some fixed dimension matrix to express a fixed dimension quantum systems. This means that the specification will be exponential size the application size because it requires the users to give an exponential matrix or some input-output vector, which is not very scalable. The second challenge is that we need a new program language that includes the loop and recursive structure to make it more scalable to large-scale program. And also, we need this new language must be feasible for automatic verification, and it is to be expressive enough to express the common feature in quantum states. The third challenge is a quantum unique challenge comes from the verification of quantum programs. This challenge comes from that the complex numbers are very common in quantum programs. Almost every quantum state or all quantum programs include complex numbers. And the complex number means that we need to deal with many nonlinear terms, such as the sine, cosine, or some E expression during the verification. And also, in some quantum expressions, there are some non-fixed terms of terms in the expression. For example, here is the expression for an n-cubic quantum Fourier transform. And from this term, we can find that it is the sum of 2 to n terms, which means that there are a non-fixed number of terms. And each term has a phase, it has an E expression. And the phase of this expression is the complex numbers. So these nonlinear terms and non-fixed number of terms are not supported very well by the existing verification tools, such as the SMT solver. So we need to find a way to encode the verification of quantum programs into some SMT solvers. So with these three challenges, we designed the framework named as QSynth. QSynth is the first quantum unitary program synthesis framework, including the recursion structures. And here is the overview structure of QSynth. The structure of QSynth is relatively simple. There are three main parts. The first part is a specification part. QSynth allows the users to give a QSynth specification, which is very intuitive to express a quantum map. And QSynth is based on a trivial searcher. It is a simple syntax-guided searcher. And these searchers will iteratively generate candidate programs based on the syntax. And in each iteration, it will send a candidate program as C to the QSynth verifier. The QSynth verifier is the key part of QSynth, and it is used to solve the most difficult part in the quantum program synthesis, is that how can we automatically verify a quantum progress? The QSynth verifier has two parts. The first one is a new language named as I², and its corresponding verification logic. And the second one is the encoding part to encode the verification process into the SMT solver. For those three challenges, QSynth includes three key new designs. The first one is that QSynth designed a new specification, and it is a new input-output style specification. So users did not need to give an exponential size matrix or exponential size input-output vector pairs to specify the target unitary matrix. And the second design is a new language and its corresponding logic called inductive squares. QSynth will utilize this logic to verify recursive quantum programs. And the third design is a new representation called parameter size path-sum amplitude form. These forms are used to encode the verification of quantum programs into an SMT solver. I want to use the synthesis of a simple GST example to show the synthesized process of QSynth. And before that, I want to introduce some basic knowledge of quantum information. The most key concept in the quantum information is the concept of qubit. For classical computers, we know that we usually operate on classical bits. Each bit can be 0 or 1. In quantum computing, there are also a similar concept named a quantum bit, abbreviated as qubit. The qubit can also be 0 or 1. The difference is that it can exist in a so-called superposition state. It means that it can be a superposition of the state 0 or the state 1. And it is a superposition, means that when we measure these qubits, it has the probability of alpha squared to be 0 and the probability of beta squared to be state 1. And in this GST example, we are going to prepare a very important and very common state used in many quantum algorithms. It is called the n-qubit GST state. n-qubit GST state means that it will put n qubits into the superposition in a two superposition state, which means that all qubits will be in 0 or all qubits will be in 1. So we usually use the map below to express this n-qubit GST state preparation. Since in practice, all of the qubits are usually initialized in state 0. So in these state preparations, we want to generate an n-qubit GST state from the n-qubit 0 states. So for the first challenge, we designed an intuitive representation for users to give their specifications. We can find, the first line is the map we want to generate. And suppose that we want to generate n+1 qubit states here. And the second line is the specification that users need to give for QSynth. It is relatively intuitive and near to the mass expression for the JHZ state. And given these states, the QSynth will compile this QSynth back to a specification used in the verification, named as the hypothesis amplitude specification. This hypothesis amplitude specification includes two parts. The first one is the hypothesis edge, which are used to specify the interesting state we are focused on. In this example, since that we always prepare the JHZ state from the all-zero state, so the hypothesis edge here suggests that the input state x will always be 0. And the second part is the amplitude function that suggests that if the input state is x, what will be the probability for the result state is in y. And with these two, so this amplitude function, alpha, exactly intuitive, if we are used to specify the desired output of the target program. And for the second challenge, we need to design a new quantum programming language that includes some loop or recursive structure, and which is still feasible to verify. So we extend an existing language named Squire. Squire is a simple quantum language embedded in quark proof systems, but there is no loop or recursive structure. So we extended it with a fixed point syntax to make it support some recursive structure. And we also developed a corresponding verification logic for the verification. In this JS example, the key part of the I-square logic is fixed point rule, which are used to verify a fixed point square program. The key idea for the fixed point rule of the I-square logic is that it tries to prove a fixed point program by induction. Suppose that we have the QSynth searchers has already find a candidate program here, this fixed JHZ fixed point function. And the QSynth verifier will try to verify that this program satisfies the user specification to prepare an n-qubit JHZ state in 2 steps. The first step, it will try to prove the candidate program satisfies the base condition, which means that the program satisfies the specification when the input argument n is less than some constant number k. And in this example, the k equals to 1. So it just tries to verify the base case in the match expression. And then the QSynth verifier will assume that this candidate programs already satisfy the specification for any input arguments when the n is when the input number is 0 to n-1. And then it will try, which means that it assumes that the recursive core JHZ n-1 here already generate n-1 JHZ circuits. And then it tries to verify that the whole program will give a result program. So it means that in here, the whole program will generate a JHZ n circuit. For the third challenge, we need to encode the whole verification process into the SMT solver. Yeah. As I have introduced, the quantum space and quantum matrix usually includes many complex number functions and matrices. Yeah. Since the complex number functions and matrices are very common in quantum programs verifications, however, there is no existing tools that can support an automatic equivalent checks between 2 symbolic complex number functions. Fortunately, in our cases, we do not need to verify the equivalence between 2 general complex number functions. We just need to verify the equivalence between a special class of complex number functions. Inspired by some previous techniques called path sum techniques, we capture some common features in many quantum unitary states and quantum unitary operations. And based on this common feature, we designed a new representation named parameterized size path-sum amplitude form. The key idea of this PPSA form is that it will restrict each unitary operations into a special form, and which makes that PPSA can decompose a complex number function from the unitary program into the combination of several integer and Boolean expressions. So to check the equivalence between two complex number functions, QSynth just need to check the equivalence between each expression separately. Since each expression is an integer or Boolean expression, so we can use the SMT solver to do this automatically. For example, during the verification of candidate JSA programs, QSynth verifier need to verify this expression under some condition. This expression says that when the input state x is 0, it tries to verify for any input y, these two complex number function, alpha JSA and alpha h are equal. And here is the expression of these two complex number function. And we can find that from their expression, PPSA can decompose these two complex number function into three parts. First, with a factorized number part, the amplitude part 1 over square root 2, and another part is the second part is a delta function. It's a Boolean function including two Boolean expressions. And also another is an E expression function, but we only check the phase part to check that whether these two phase parts are equal. So with these techniques, we can encode the quantum verification of a quantum program into the SMT solver. So for the evaluation part, we also demonstrate 6 additional case studies of QSynth in our paper, and we also provide out the output Qiskit program compiled from the I2 programs in our paper. And for the evaluation, we want to compare the synthesize times of QSynth with the existing quantum circuit synthesis technique. We collect 10 benchmarks from many array of quantum computations. These quantum benchmarks are in 3 categories. They are from arithmetic circuits and from quantum state preparation and some subprograms widely used in many quantum algorithms. And we compared QSynth with two existing quantum circuit synthesis framework. They are QSynth and QFast, proposed in 2021 and 2023. For the previous framework, QFast and QSynth, we used their specification interface to test their synthesis time for different synthesis tasks. And for each framework, we test them under different application size from 3 to 6. From the result, we can find that for the QSynth, we just need a constant time to generate a result program for any size of the applications. But for QFast and QSynth, we will stop their synthesis and regard the synthesis as failed if the running time is over 1 hour. And the result shows that the QFast and QSynth exactly their execution time will be increased exponentially when application size is increased, and they fail in all of the synthesis tasks when the application size increased to 6. But for the QSynth, for our framework, it can successfully generate all the synthesized program in a constant time. That's all for my talk, and I'm here for any questions.
Thank you for the nice talk. Do we have any questions?
Thank you for the talk. So I was a little bit confused about, you said, we don't want to synthesize a matrix because it's too concrete and it would be exponential.
Yeah.
And then you said instead we want to have some sort of input-output description. But the input-output description you showed was just the action on a single vector, which was all 0, at which point, we're essentially just, if there's just a single input, it doesn't tell us all that much, and there could be multiple matrices that correspond to that. And, if we only care about the action on all 0, then we could just show a we're just synthesizing a vector effectively. So can you specify multiple inputs and their outputs? Can you specify full path sums as the input to this?
Yeah, if for a more complex example, the key part is to suggest that exactly the syntax of the QSynth spec include sum expressions. So you can use the sum expression to specify the specification for like the quantum Fourier transforms. And also another way to specify the specification for a more complex example is that you can use the users can use this hypothesis amplitude function to specify the expression. And for example, for the GIS expression, the function alpha here will suggest that when the input is x and output is y, the amplitude here use this function to express the term here. So if the users want to specify a symbolic matrix, you can suggest that for a matrix that when the index is indexed by x and y, the entry of the index x and y can be specified by the function alpha. So then they do not need to give expander size matrix. They can use the complex number functions to specify this matrix.
Thank you. I think we can take one more question.
Thank you for the nice talk. You did not talk too much about search procedure.
Yeah.
Is that anything noteworthy or just a simple enumeration-based search? And in your experiments, how many iterations it takes to get a solution?
Yeah, our search is a very standard syntax-guided search, but we believe that many search optimization techniques can be applied. But in this framework, we first just used a very simple syntax-guided search with a depth bound for the program, and we will stop the synthesis if the search exceeds the depth bound. It's like we set the depth. It is a wide first depth, and we stop the search when the depth will exceed 7. The syntax steps. It's a syntax guided step.
All right. We can take more questions offline. Thank you very much once again, and welcome to the break.